Okay, so this lecture goes with chapter 13 in the OpenStax textbook, and it's really kind of the opposite of what we did the other day. It's the control of microbial growth. And so we're going to talk about some general principles on control and then talk about why you might select one method over another, and then talk about an overview of several specific methods. And controlling microbial growth is a really common problem. Just like we want microbes to grow in some areas, in other areas we don't. And so I've got a picture of canned pickles here. Pickling is a typical way of controlling microbial growth. So this is a picture from your textbook. It just using swabbing, they identified the number of microbes on a per centimeter of a car surface, and they looked, and not surprisingly, areas that people interact with a lot had a lot of microbes. The steering wheel, the door latch, the door lock. Microbes are in a lot of places. And microbes, even areas that we don't interact with, there's still lots of microbes growing there. So, what's important when we want to control microbes, and what do we do? Well, a lot depends on the type of microbe that's there and what stage it is in its life cycle. Um, the characteristics of the microbe, the number of microbes present, characteristics of the environment matter, whether there's a lot of organic matter, what temperature you're going to hold this thing at, and if the microbes have formed a biofilm, things like that. And what is the risk of infection or damage to the material that's surrounding the microbes? In general, the most resistant microbes that we ever have to deal with are prions and endospores of bacteria. Um, Mycobacterium, TB bacterium are tough. Um, Non-growing forms of protozoa are tough. But there's lots of microbes that are pretty easy to control, that fall apart pretty quickly with just a little bit of control effort. A lot of the viruses and gram-positive organisms are actually not that hard to get rid of. Okay, in all cases, it's important to know that microbes, one of the key things is time. No method will work instantaneously. It takes time to reduce the number of microbes in a population. If a control agent can get rid of 90% of the microbes in a minute, it's doing a good job. But to get rid of all of them, you have to take some time, and so often you need to use time to let things work. Okay. In general, we divide methods of control into two big groups: chemical methods, and these chemical methods may sterilize a substance, or they may be used to treat or prevent infection, so they might be used on the skin. Um, but there's lots of different chemicals that I'm going to talk about. And then the other methods are physical methods that don't involve exposure to chemicals. These are changing the environment, changing pressure or the availability of water, or using radiation or filtration. Um, this picture here is of a UV sanitizer that's used in a hospital room. It blasts UV light to control microbes on surfaces. Okay, so we're going to start with these physical methods of control, and probably the most commonly used methods are heat. Okay, we use particularly moist heat, like steam, steam under pressure, above the temperature of boiling, and we do this because it penetrates well. And these are, in the microbe lab, this might be an autoclave, which we use to sterilize our media or to get rid of our wastes. Or in food, we use moist heat in canning. And so we again use pressure and moist heat, and that can kill most organisms. The hardest thing that happens in canning is that we have to kill endospores. And so that means we have to heat things for a long time, well above boiling, the temperature of boiling, because endospores are pretty tough. But in many cases, we don't have to heat that high. In some cases, like pasteurization, we just have to heat things high enough to kill growing forms of spoilage organisms and to kill not just growing forms but resting forms of pathogens. And so this is usually 70 degrees heat because these are usually just mesophiles, and so they're often killed by pasteurization. You may get spoilage still, and spoilage organisms may survive, but we can often, this is good enough. And so here's high temperature pasteurization, and here's ultra high temperature pasteurization. This is very, very quick, but then the material lasts a long time. We also use dry heat. This, like with our wire loops, we heat well past boiling to incineration, and so that's flaming. But this is also another method. Of course, with heat, you can change the substance. So if you're sterilizing milk, you're likely going to change its taste and its texture a little bit as well. Okay. We also use cold to stop microbial growth. And we can stop all microbial growth at temperatures below -70. Won't kill the organisms, but it prevents them from growing, and so that's often good enough. Likewise, we can use desiccation. We dry things out so much that microbes really can't grow, and so dried fruits, dried vegetables, even dried meats, as long as they're kept dry with high concentrations of salt or even high concentrations of sugar, those things won't spoil. So works fairly well. And again, this probably won't kill organisms, but it prevents growth. Another way of controlling microbes that's a physical way is by having filtration. We make filters that have small enough pores in them that microbes can't get through. This may intercept all bacteria and even viruses. So we can say what size we think will work, and these filters are tested and used. And the nice thing about filtration is here we're not altering the temperature or any other quality of the air or liquid that passes through filters. So we can use membrane filters to sterilize solutions. Although, again, these solutions have to be pushed through under pressure, and these filters have to be very, very fine. Another method is the use of radiation. Radiation, ultraviolet radiation, causes changes to DNA, the formation of these thymine diners, that if enough of these form, it will kill a microbe. Okay. Again, this can have effect on people. This is not so great for people. And this can also change the quality of materials. And UV light in particular doesn't penetrate well. But in other cases, we can use gamma irradiation, which has larger particles. And these particles pass through most foods and, again, damage DNA. And so we can do this, and the doses that we can do here are good enough that we can basically eliminate all pathogens and most spoilage organisms. This doesn't mean the food ever becomes radioactive. It just means that anything in there has their DNA essentially cooked, and so can't reproduce. Okay, there's a bewildering number of chemical agents. Okay, generally these are all going to change the permeability of membranes, damage the proteins or damage nucleic acids of the microbes, and so render them unable to reproduce. Okay, the key thing is chemical agents. Like you really can't use many chemical agents in food because they might be toxic to us, or they may change the quality of the food. Some are so damaging that you can't use them anywhere people are around. Certain sterilants like bleach or hydrogen peroxide or ozone, they're very reactive, and so we can't use them on people's skin even. But others, like antiseptics, This is betadine here being rubbed on a site where a person's probably going to have their skin punctured to either draw blood or give them some fluids. Those antiseptics are fairly non-toxic. Okay, I won't go into all of them here. There's many, many. Remember when we talked about Lister? Lister used phenol. It's got a carbon ring with an alcohol group on it. Okay, and these are very good at disrupting plasma membranes. And there's a bunch of different types. We also have heavy metals that we use. Heavy metals are generally going to change the shape of proteins, and so enzymes won't work. Protein pore channels will change, and so they'll be hard on organisms. We also use halogens like iodine or chlorine. These again alter protein synthesis and change membranes. Some chlorines are strong oxidizing agents. They're dangerous in that they react with almost anything. An example of kind of a phenol and an iodine molecule is this betadine. Okay, a very nice disinfectant, very effective. It just, things can't grow on it, but we can use it on the skin. There's also other things we can use on skin like bisphenols and hexachlorine and triclosan. These are really good for the hospital. We don't really need anything this strong in our houses, but in the hospital, these are really helpful. What's more useful for us are disinfectants that are less toxic, that we can use on skin surfaces and other surfaces, and that can easily be removed. Good examples of these are ethanol, and then soaps like detergents or surfactants or quaternary ammonias. These are really good at degerming or sanitizing. They're not really strongly bactericidal, but they'll help remove things and get them off surfaces so that we can use them. Okay, and so other chemicals are more mild and they inhibit growth, like many organic acids. I talked about pickling. That's acetic acid. Benzoic acid we add to a lot of food. Sorbic acid, vitamin C. We can do that. Nitrites, like, are added to bacon and other sausage meats. Those are nice. There's some association with toxicity there. And then we have other, kind of at the opposite end, we have sterilants that are gases and plasmas and kind of supercritical fluids that we use with medical devices. Okay. So with all these, kind of know what a chemical agent is and be able to give me some examples of chemical agents. Know why a soap is good, even though it doesn't kill many bacteria, washes things away. And know that that many things that have poor activity against the most extreme organisms are still useful, because things like endospores and microbacteria aren't that common. We test these things all the time, using similar methods to what we use to test antibiotics, and even some of the things that don't have big zones of inhibition are quite useful. And there's other methods as well, using like this use dilution test. So we control microbial growth in many, many places: hospitals, food industries, schools, and daily life. What really matters is deciding what is the most important criteria here, what kind of microbe is likely to be present, and how much do I need to reduce that microbe or eliminate it. Okay, there is a quiz open on Chapter 13 that you'll have over a week to do. After today, we're going to start on DNA. And so sorry for the short notice on not having a lab, but sometimes things come up.